Good afternoon, everyone. Today we'll be talking about our hands-off digital palatal expander. We are team Expanding Horizons, and our team is Jay Beto, Hannah Bach, Liz Miller, and myself, Marissa Press. So a little bit of background. A palatal expander is an orthodontic device that are used in pediatric patients to create more space in their mouth for orthodontic appliances. You can see the expander in the mouth of the child on the right. And then on the left is this tool, sometimes referred to as a key, that is used to enable the expander to widen the patient's mouth. So in the expander, there's this tiny hole, maybe that's a millimeter wide, and this key, which you can see the tip is very tiny, has to fit into and then turn in order to expand the device. This can be unreliable, and also you don't know if the device is always that the key and the device have always had that interface. It's a hard angle, so the child can't always do it by themselves, so they have to rely on a caretaker, and sometimes caretakers forget. So then the device is not be expanding as much as it should, prolonging the patient's treatment. So with this, we developed a problem statement. To develop a mechanism for widening a palatal expander in specific increments over a measured period of time while minimizing patient contact in comparison to current models. So with this, we mean specific increments, as in the orthodontist can know exactly how much the palate is expanding by, and then minimizing patient contact. Like I said, the patient can be unreliable at times, forgetting to turn their device every single day, or however often they need, so we want to try and minimize as much as they have to do that. So we developed some feasibility and merit criteria. For feasibility, we want to limit patient interaction, we want measurable increments, and we want the device to be safe. By limiting patient interactions, which is also mentioned in our patient criteria, we want to try and remove the need for the key and have the device expand on its own. That way the patient doesn't have to remember to turn the device every single day. Measurable increments, like I said before, we need the device to turn in specific increments so that the orthodontist can keep track of the process. And then obviously the device needs to be safe, as this would be going into the patient's mouth. And for the rest of the merit criteria, there is space, adaptability, and cost. For space, since the device would go into the patient's mouth, we do not want it to be too big. The patient has to be able to easily breathe, to comfortably eat, and just overall not be bothered by the device. For adaptability, the device sometimes is used with other orthodontic devices such as braces, so the device needs to be able to be attached or work with other orthodontic devices. And then cost, because we do not want to go too high in cost, otherwise orthodontists and patients would not opt for this device.
With this criteria in mind, our final design is hands-off, a digital palatal expander. Our hands-off palatal expander works by having our Pocket Orthodontist app communicate with our circuit subsystem to cause the motor to turn. As the motor turns, the gear will turn a double-threaded rod that will cause the device to expand outward in 1/4 millimeter increments. This device will connect to the molars of the patient, and as the device expands over a long period of time, it will widen the palate of the patient. The device can be in the patient's mouth sometimes up to 6 months or longer, so it is important that the device is able to last this entire time period. And with that said, I will now talk a little bit more about the mechanical housing subsystem. The housing subsystem is responsible for causing the physical expansion of the device and also for isolating the mouth from potentially harmful components. The actual expansion of the device is done using a double-threaded rod that is threaded in opposite directions on either side. There is one threaded hole on each of the two main bodies that the rod will be threaded into. The gear that is attached to the double-threaded rod will mesh with the gear on the motor, and as the motor turns, it will turn the rod, which will cause the actual device to expand. The testing that we have done has shown that the gears are able to remain meshed throughout the entire process. The device also contains two support rods that are located on both sides of the double-threaded rod. These two rods will slide freely within the two holes and help give the device more support and strength. The device contains tooth bands that will connect to the patient's molars and will help to expand their palate. In order to help protect the patients from potential harm, the top layers of the main body have a thin layer of acrylic to help protect the user from electric shock. The last component of the housing subsystem is the biocompatible shield. The biocompatible shield helps to isolate the device from the mouth and the patient and also doubles as a mechanical safeguard to prevent overexpansion of the device. The shield is a watertight acrylic piece to help prevent food or water from getting into the device and causing issues, and also prevents any components from the device from interacting with the patient in any unintended way. The shield also doubles as a mechanical safeguard by attaching to one of the main bodies and extending 15 millimeters past the face of the other main body. The maximum distance we would want the device to expand is 15 millimeters, so having the device expand that far beyond that face, it would be another way to help prevent the device from overexpanding.
Hi, my name is Liz, and I will be explaining the interaction between the housing and circuit subsystem, and then I will be going into detail of what the circuit subsystem consists of. So Jay just explained the housing subsystem and components, and like I said, I will explain the circuit subsystem in the next slide. But we just wanted to have a segue between the two, showing the interaction of the housing and circuit subsystem, especially since this is the only physical interaction between the subsystem, because there's no physical interaction of the programming subsystem and the circuit subsystem. So we have our biocompatible shield, which protects the circuit subsystem and the expander from any outside particles such as food or saliva. We have the electrical tape that is holding the circuit subsystem in place on top of the expander. This is to ensure that nothing interferes with the meshing of the two gears, and also to ensure that the meshing of the two gears is continual as the expander widens, so that it will always widen on time, and always widen that 1/4 millimeter turn when it needs to. The electrical tape also serves as a protective material for the circuit subsystem itself, so that if there were any external particles such as food or saliva to slip through the biocompatible shield, it would not interfere with the circuit subsystem's job, and so it would not cause the circuit subsystem to short circuit or malfunction. This electrical tape also serves as a protective safety feature for the patient, so that if the circuit subsystem was to come loose, there would be no concern of any of the electrical components touching the metal and causing a discomfort for the patient, due to the buffer that the electrical tape serves. And although there is a plastic cover between the metal expander and the circuit subsystem, this is just another extra precaution to ensure that the patient is not injured or experiences any discomfort due to the circuit subsystem. So here we have a closer look of what the circuit subsystem consists of. So on the right is the same picture as before, so it shows how the circuit subsystem goes into the device, and then on the left is the close-up picture of the circuit itself. So we have our battery pack, which consists of 8 AA lithium batteries that power the DC motor and the Arduino. We have the DC motor with an encoder, which has the gear attached to the end of it, and turns whenever the Arduino sends a signal, which is based on the programming system, which Hannah will go into detail later. But this is the DC motor is what widens the expander and causes the pallet to widen, so it supplies enough torque, which supplies enough force to widen the pallet. And so we also have our Arduino Nano BLE, which sends signals to the DC motor, telling it when to turn and when not to turn, again based on the programming subsystem. But it does this by receiving an input signal from the encoder on the DC motor, and based on that signal it sends an output signal to the H-bridge, and then the H-bridge sends an output signal to the DC motor, telling it to turn or to stop turning. So there's also the safety feature of the circuit subsystem. So there's a button on top of the Arduino, and there will be a button that leads to the enable line of the H-bridge. So when these two buttons are pressed, it actually stops the circuit from working. So these buttons would be pressed in emergency circumstances only. So if there was a malfunction of the motor, and if the motor would continually turn and would not stop and cause discomfort for the patient would press these two buttons and stop the whole circuit from working. Unfortunately, there's no way to restart the device, so the patient would have to call their orthodontist, inform them of the malfunction, and the orthodontist would have to replace the expander in the patient by removing the current expander and replacing it with a new one that functions. And so with that, Hannah will explain the programming subsystem.
Hello everyone, my name is Hannah Bach, and I'll be going into further detail about our final subsystem, which is the programming subsystem. This is the means by which the orthodontist interacts with the expander and is composed of two parts, the Pocket Orthodontist app on the left, and coding that is internal to the Arduino, which you can see on the right. The user opens the Add a Treatment page from the home screen, connects to the device via Bluetooth, and submits two numbers. These are the two metrics that determine treatment, time between turns and total duration, and are transmitted to the Arduino BLE chip via Bluetooth. These variables then run the code that is internal to the Arduino chip unless a new treatment is transmitted, and then those new variables supersede the old ones, and so on and so forth. When the code is running, digital pulses are sent to the encoder and motor portions of the circuit subsystem to initiate expansion when necessary. During the testing phase, we ran test code to ensure that physically unsafe instructions were rejected and to make sure commands sent to the circuit subsystem were reliable and repeatable. In terms of the device as a whole, this subsystem allows for remote adaptation and removes patient interaction entirely from the process of expansion. So you can see our final budget was $323, distributed approximately equally between both the circuit and housing subsystems as shown. The programming subsystem used Arduino and free app development software, so it didn't require any purchasing. For a true production model, this cost would be greatly reduced as the device would be significantly smaller.
In revisiting feasibility and merit criteria, so we achieved all of our feasibility criteria. There's no patient interaction whatsoever. Once the device is in the patient's mouth, it is good to go. Measurable increments, because in the app, the orthodontist can put in exactly how much they want the expander to widen by, and they can keep track of that. Safety, the device is safe. We are using biocompatible materials. We are trying to isolate all the circuitry as much as possible. Obviously in these pictures it is not, just because we wanted to be sure that you can see it in the demonstrations. And then also built into the app are some checks just to make sure that the orthodontist does not accidentally type in a number that is physiologically large. And looking at the merit criteria, we say we met our patient interaction because we have no patient interaction once it's in the mouth. It's good. Space, adaptability, and cost, there are these yellow circles by, just because when we developed this criteria, we were thinking of a true to size model, and so since our device is bigger, we can't accurately say if we have met those criteria, but we also cannot say that we have not met the criteria, so those are getting yellow circles. So some conclusions and recommendations. In conclusion, the device is functional, and if placed in a patient's mouth, it would, in theory, widen the patient's upper palate. There are still some recommendations that we have for future iterations. So the first one would be to construct a properly sized model, and that would be able to happen once there is the proper technology available. One thing that we had wanted to do but didn't quite get around to was to connect the app and the circuit via Bluetooth so that there is no physical connection between anything. The orthodontist would have just used the app and then the device would have responded. But just due to time and then the circumstances of this quarter, we did not get to do that. And then also we would like to implement further safety features. While we do have some, you can never be too safe. And so this would include optimizing the emergency stop button that was previously mentioned. We want to make sure that it's in a location that the patient won't accidentally set it off, but that they can easily reach if it was needed. and also making sure that device stops completely until they can see their orthodontist. And so, does anyone have any questions?